So we have this series, and I've represented the individual summands as these rectangles, and it looks like every single one of them is beneath this curve. For this series in particular, the curve I've got is y equals 1 over x squared. Well, how did I get that? All I did was I took the formula for the series, right, 1 on n squared, and I said, well, I could probably do that formula for numbers which aren't just integers. I could do that for any real number x. But if I wanted to compute the area underneath the curve, well, that's a job for integrals, and not just integrals, but it would be an improper integral. So I would have to start my integral at x equals 1, right? I have this infinite discontinuity at x equals 0. I can't start my integral there. But I could start at 1 and try integrating out to infinity. So I would be ignoring this box right here. So whatever I get for this integral, I would just have to add 1 to it. And this improper integral actually converges to a value of 1. So is there a finite amount of area contained in all of these rectangles when I put them together? Yes. How much of it is there? Less than 2 units of area. So I don't have an exact value for this series, but now I know it converges based off of being able to calculate an improper integral. So all I'm doing here, again, is I take the formula for my summands, I treat the variable as a continuous variable x instead of the discrete variable n, and I compute this improper integral from 1 up to infinity, integrating the formula from my original series. Now, what I'm doing, so this series here is bounded, and since each of the summands is positive, the partial sums are all getting bigger. So the limit of the partial sums, well, the partial sums are an increasing sequence. They are a bounded sequence. So bounded and increasing means that that sequence of partial sums has to converge. Let's try it again with a different series. This time I want summation of 1 divided by the square root of n.